in this question. What is NAND completeness, and what is the enumeration of all possible Boolean functions? Well, let's take a look. NAND completeness is the idea that any Boolean operation can be represented by NAND. And so, if I write a NAND function here, and then I go ahead, I can represent any other function. I can represent not using NAND by just saying, well, not is just NAND of a Boolean input with itself, right? And we can go ahead and let's check this. We can see that when given an entire truth table of all possible inputs of A and B, NAND gives us this pattern. Well, what does not give us? Not gives us, we're doing not A specifically, it gives us false, false, true, true. Well, since we have this NAND not function defined here of NAND A and A, let's see what this evaluates to. That also evaluates to false, false, true, true. What about and? How would we represent and? Well, an and represented just in Python syntax, we have our column A and our column B. And in NAND logic, we have the NAND of A and B, NAND the NAND of A and B. So it's a little redundant, it's more verbose, but this idea that NAND is what we call functionally complete is a great way for us to go about even potentially simplifying Boolean expressions, identifying groups that are redundant or can be removed, or pairs that can be simplified. And so we can use this idea of NAND completeness to realize and recognize that Boolean expressions aren't very complex. There are many options that we can choose from, but they can all be represented by one operation with a little bit more complexity. With that being said, well, how many Boolean operations are there? Well, turns out there are 16 different Boolean operations. And we calculated this just by using a little bit of combinatorics, right? And we said that, well, our data is the product of true and false repeated 4 times, right? Because in our standard truth table of a single operation, we have 4 outputs. All those outputs are represented by true or false. What are the different ways that we can represent those outputs? How many different ways can we produce the product of true and false if we have 4 different outputs? Turns out 16. And we can represent that just by doing n squared, where n is 4, and we were choosing 2. And so we end up with a longer truth table where our inputs are actually our columns. We've kind of transposed this table, and we have 16 different rows representing every possible way that you can combine true and false. And so you assume that there has to be some functions that evaluate A and B to be these rows. Well, let's go ahead. Let's enumerate some of the ones that we know, some of the ones that we've covered. Well, there's and, right? And is pretty straightforward. It's A and B. There's or, that's just A or B, just regular Python syntax here. There's XOR, which is the exclusive OR, which isn't represented inherently in Python, but we can derive it. There's NAND, which we've covered, which is the negation of A and B. There's not A, okay, fairly straightforward. There's not B. We have the implication. We have the bidirectional implication. A lot of these operations are named. And so what we do is if we take our original data of all the possible different ways we can arrange them, and then we go through each of the functions that we've written above, we apply those functions to our data frame, and we check. So we evaluate, and we apply, and then we check where in our data frame exists that row such that the output of our function matches that row exactly. And using index max here on a Boolean output is a shorthand way of saying my output's Boolean, give me back the name of the row or the the name of the row that has the first value of true. And so we're able to find rows that exactly match this function output, and we can store this in a dictionary. We can update the name of that dictionary from the function name itself. So let's go ahead and evaluate this and see what we get. Looks like we've matched every single function we've defined. Right here we have the row that corresponds to the inclusive OR. Right here we have the bidirectional implication, the regular implication, the AND. We've found NAND. We found the exclusive OR as well. And all of these so far after spot checking looks like they're accurate. But Well, what about all these unnamed positions, right? We have 0, there's still 3, nothing matched this, and nothing matched 5 or 6, so on and so forth. What are these? Why do we not talk about them? Well, it turns out that we don't talk about them because they're really not as interesting. It turns out that row 0 corresponds to just true, right? The output is always true, so we don't care about A or B, it's just always true. Row 3, well, it turns out that's just A, right? Wherever A is true, row 3 will also be true. Row 5 is B. Row 6, this one's interesting, it's equivalence, right? Whenever A and B are the same, whether they're true or false, we return true. And then we have these other ones like NOR, which is only false and false, and then 15, our final row, right? Everything's false, so we don't care about A or B, it's always false. And we can use these to further update our data frame. We see that there's a couple more uninteresting, really unnamed functions here, but there are many different ways to combine them, and in Python, we really only use 3. We use not, we use and, we use or. And this idea of being able to express our Boolean logic in many different ways using a restricted vocabulary is what makes them so interesting.